Welcome all. So, we will continue today with our analysis and design subjected to blast and impact loading. So, last time we dealt with the response of a system subjected to a pulse loading. So, we will continue the formulation and look into the analysis procedures. So, today we will be looking into the half sine pulse. So, we will be doing the same procedure that we followed for a pulse type of loading. Okay. So, how we solve this problem? Okay. First, we looked into our real life example. Okay. We had been given a real life beam. Let us say we are taking a real life beam, or it can be any similar structures. From there, we make our mathematical approximations. Okay. We represent this thing using an Euler-Bernoulli beam or a similar formulation. Then we approximate the boundary condition. Okay. So, let us say we are doing this for a simply supported case. Okay. So, from the real world we have changed into our mathematical world. Okay. So, this was the real world, now we are in the mathematical world. Okay. Then we looked into the application of our loading. Okay. So, in case of blast we have seen that we are approximating the loading using a planar wave. Okay. Okay. So, this planar thing is applied to my entire system. Okay. And it can have different time signature. Okay. So, last time we looked into the pulse type of loading. Okay. So, right now we are looking into the half sine loading. Okay. So, this is the time signature of the loading. Okay. So, since this is my special distribution of the loading, we are taking the first mode, assuming the first mode is contributing the maximum. So, this is the first mode contribution, and the degree of freedom, we are choosing the degree of freedom at the center. Okay. So, y vertical at center we are choosing as my degree of freedom. Okay. So, from there we make our shape function. Okay. So, denominator part is the deflection equation. Okay. Deflection equation, and the numerator part is the deflection equation. The denominator part is the deflection equation at center, evaluated at the center. Okay. So, this will give a signature of the mode shape, and this will give me the signature of the chosen degree of freedom. Okay. So, once we have our mode shape functions, from shape functions we can calculate our m star, equivalent mass, equivalent stiffness, and equivalent force. Okay. Using the standard equations that we have. Okay. Or we have given the table also. So, we can use those table also to calculate the different quantities. Okay. So, same thing we are going to get from the both the parts. Okay. Okay. So, once we have our equivalent mass, equivalent stiffness, equivalent forcing functions, then we change this thing into our this single degree of freedom approximation, and from there we draw our free body diagram. Okay. So, we are using D'Alembert's approximation. Okay. Okay. And normally in case of blast and impact loading, what we are doing is that we are ignoring the effect of the damping. Okay. So, once we ignore the effect of the damping, we can write our equation of motion. Okay. So, this equation of motion will have two parts, one when my loading is being applied, and one when the loading is removed. Okay. Okay. So, the first part we can treat as a loading during the forced function and loading during the free vibration. Okay. Okay. So, after that what we do is that we calculate the response of the system in the two phases. Okay. During the forced phase and during the free vibration phase. Okay. So, in both the phases, okay, the response of the system is in two parts. Okay. The response of the system is in two parts, a steady state response and a transient response, or U particular plus U complementary, they are the same thing. Okay. So, the total response is, for the particular part, it will be a signature of the forcing function divided by my equivalent stiffness, okay, and in the transient or complementary part it will be a signature of the frequency of the system. Okay. So, this is when the system is in the forcing part, and the initial condition we are assuming that the system is at rest. Okay. So, the initial displacement and velocity is 0. Okay. After that, once the forcing function ends, okay, the effect of the forcing functions end, we again write down the solution for the part. So, here since the force has been removed, the particular part becomes 0 and only the complementary part remains. Okay. Okay. And the final condition for this part. Okay. So, whatever is the final condition, u at time t equals to Td is equals to u naught, let us say, and the velocity at time t equals to Td, okay, let us say u dot naught. Okay. So, this two final conditions from the first phase we will use as an initial condition for the second phase. So, final condition from the forced vibration phase will be used as a initial condition for the free vibration phase, and from there we can calculate our A2 and B2. Okay. So, in this way we calculate the response of the system in the two phases. Okay. And then we normalize the responses, okay, with respect to the static response. Okay. And after we have done this thing, okay, what we do is that we calculate the maxima in the two phases. Okay. We calculate the maxima, okay, during the free vibration phase, we calculate the maxima during the forced vibration phase. Okay. U max forced we calculate and U max free we calculate. Okay. How we calculate it is that we differentiate it, okay, and we equate it with 0, and whatever is the time we are getting we put back here and we get the U max. Okay. And similarly we do for the U max for the free vibration phase. Okay. So, here what we are showing is the, depending upon the different ratio of time of loading Td and the natural period of the system, okay, we have calculated the maxima response of the system during the free response phase and during the forced response phase. Okay. And after that we plot the envelope, okay, we plot the total envelope, okay, that will give the overall maxima. Okay. So, this curve we can directly use, okay, because this curve is made after doing all this approximations. Okay. All this equation, the solution of all these equations will at the end of the day give me this curve. Okay. And this curve we can directly use for the design purpose. Okay. So, what we need to do is that we will have the time of loading of the system, we will have the frequency of the system, okay, we will calculate the response factor, okay, of a single degree of freedom system subjected to a half sine pulse loading. Okay. Then we will multiply with the U static quantity. U static quantity will be given by the equivalent force divided by the equivalent stiffness. Okay. And this will give me the U max directly. Okay. So, we can use this curves directly in order to calculate the response of my system, response of a single degree of freedom system to an half sine pulse. Okay. Similar to what we did for this type of pulse system. Okay. Similarly, the same treatment for a triangular pulse system. Okay. So, for a triangular pulse system also, how we got this thing? We started from a real life example. Okay. Let us say for a beam. Okay. So, this real life example we changed into a mathematical beam, okay, or a cantilever depending upon what we are doing it. Okay. We assumed a planar distribution of the loading. Okay. We assumed that the maximum response is given by the first mode, okay, and the maximum displacement is occurring at the center. Okay. From there we calculated our m star, k star and p star. Okay. We made our system. Okay. We made our equivalent system. Okay. And from the equivalent system we wrote down the equation of motion, okay, into two phases. Okay. We ignored the damping and we wrote down the equation of motion in two phases. Okay. In the forcing phase where time t equals to less than Td, okay, sorry, when time t is less than Td and when time t is greater than Td. Okay. So, this becomes a forced vibration case and this becomes a free vibration case. Okay. We wrote down the response u particular plus u complementary or u steady state plus u transient. Okay. We calculated the maxima, okay, of this function in the forcing phase also, forced response also, the maxima in the forced response phase also. We calculated the response in the free also, free phase also, and then since we have the value of u max, absolute u max, okay, and that will be a function of static response, okay, that is u naught and Td over Tn. Okay. So, we plotted this function out here. Okay. So, and from there we can have the envelope which will give me the overall maxima response. Okay. So, using this procedure we calculate the absolute maximum response of the system subjected to a triangular pulse loading, okay, and this will be depending upon the static response as well as the time period of the loading and the time period of the structure. Okay. Here one thing which needs to be seen is that in this particular treatment, okay, what we have done is that we have chosen first mode and the deflection y max at center, okay, because for this particular case, okay, let us say we are showing this for a simply supported case loaded with a planar condition. Okay. So, this is our first choice of my mode, that is we are choosing the first mode and we are choosing the maximum deflection at the center. Okay. Let us say, and from there what we are doing is that we are making our shape function. Okay. So, the numerator of the shape function is given by that particular deflection equation. Okay. In the simply supported case it has been given by the deflection equation for the simply supported case, and the denominator is given by the deflection equation evaluated at the center. Okay. And from this shape functions we are making our m star, k star and p star. Okay. That is the equivalent mass, equivalent stiffness and the equivalent force. Okay. Let us say we have a different system. Okay. Let us say we are dealing with a cantilever type of system. Okay. So, this was our system. Okay. So, we have been given a cantilever system. Okay. So, this will be my approximation of a cantilever. Okay. So, when we are dealing with the cantilever, we can choose the degree of freedom at y max at end. Okay. So, the degree of freedom becomes the deflection, maximum deflection at the end, and this becomes my mode shape. Okay. And from there again the shape function will change. Okay. So, the numerator will be the equation of this cantilever motion, and the degree of freedom will be the value of y evaluated at the end. Okay. So, similarly if our system is a fixed beam, okay, a fixed beam, then again this equation will be the deflection equation for a fixed beam and it is evaluated at the center. Okay. Similarly, we can choose our degree of freedom wherever we want. Okay. So, that will be reflected in the denominator. Okay. So, in this way we can choose the required degree of freedom and we can choose the required mode shape. Okay. So, the effect of the required degree of freedom will be shown in the denominator, the effect of the required mode shape will be shown in the numerator. Okay. So, using this equation of the shape function, okay, equation of the shape function, we can choose any degree of freedom required and we can choose any shape function required. Okay. And corresponding to our choice of our degree of freedom and or our choice of mode shape, the shape function will change. Okay. And that will have an effect on the equivalent mass, equivalent stiffness and equivalent force. Okay. So, those effects will be translated over there. Okay. So, for any given system we can choose any degree of freedom which we require and we can choose any mode shape, okay, which are of our interest to us. Okay. So, we just need to change the corresponding deflection equation and or we can choose the point where we are calculating the degree of freedom. Okay. The mode shape effect will be shown in the numerator, the effect of the choice of the degree of freedom will be shown in the denominator. Okay. And using all these approximations we can directly calculate the response of that particular given system subjected to any type of loading. So, we have dealt with pulse loading, we have dealt with half sine loading, right now we are showing the triangular loading, okay, and this is the response curve that can be directly used, okay. Moving ahead. So, the effect of the pulse shape and approximate analysis for the short pulses, okay. So, now we are looking into the effect of the different pulse shapes that we have taken, the triangular pulse shape, the half sine pulse shape, the rectangular pulse shape, the half sine pulse shape and the triangular pulse shape, okay. So, if the pulse duration Td is longer than Tn divided by 2, okay, it means that Td, okay, the time of duration of the loading is longer than half of the natural time period of the system, the overall maximum deformation occurs during that pulse, okay. Then the pulse becomes of greater significance. If the value is large, okay, if the value of the ratio of Td over Tn is large, then this overall maximum is influenced by the rapidity of the loading, okay, how fast the loading is being applied, okay. The rectangular pulse in which the forces increase suddenly from 0 to P naught produces the largest deformation, okay. Here there is a rapid change in the loading. So, here we can see, if you look into the envelope, okay, it produces the maximum response, okay, it produces the maximum deformation, okay. The triangular pulse in which the increase of the force is initially slowest among the 3 pulses produces the smallest deformation. Here the rate of loading is slow, okay. So, thereby it gives me the least increase in the displacement, okay. The half cycle sine pulse in which the force initially increases at an intermediate rate causes deformation that for many values of Td over Tn is larger than the response to the triangular pulses, okay. So, if we looked into this pulses, we can see for a large number of range of T over Td, the response of this system is more than that of the triangular loading, because if you look into the total impulse out here, okay, the value of those impulse will be more than if we try to calculate the impulse out here, okay. So, the rate of loading, okay, the sudden rate of loading is more out here. So, it will produce a greater increase in the deformation, okay. If the pulse duration Td is shorter than Tn over T2, okay, it means if the loading pulse is shorter than half of the time period of the structure, the overall maximum response of the systems occur during its free vibration phase and is controlled by the time integral of the pulse, okay. If Td is shorter than this value, okay, then the maximum will occur in the free vibration phase, okay. This can be demonstrated by considering the limiting case at Td divided by Tn approaches 0, okay. If you looked into the left hand side curve, as the pulse duration becomes extremely short compared to the natural period of the system, it becomes a case of pure impulse of magnitude, okay. So, it means that if we are in this range, okay, as we are approaching the left hand side range, okay, this becomes a case of a purely applied pulse, okay. Okay. So, the response of this system to this impulsive force is the unit impulse response, okay. So, this is the response of the system, okay. So, this we are showing using a Duhamel's integral, okay. This has been shown using a Duhamel integral, where the maximum deformation is been given by this equation, okay. Okay. So, the maximum deformation due to the rectangular impulse of magnitude I equals to P naught Td is this much, okay. Due to the half cycle impulse, this becomes 4 Td over Tn, okay, and the maximum response due to a triangular pulse is this much, okay. So, this is twice pi, so 2 into 3.14, this is 4 and this is pi, so 3.14, okay. Okay, so this is approximately 6, 4 and 3, okay. So, the increasing order of magnitude, okay. So, here also we can see, if we go by this range, okay, there is an increasing order of magnitude, okay. So, here, okay, you can see the increasing order of magnitude, okay. This pure impulse solution which vary linearly with Td over Tn are exact if Td over Tn equals to 0. For all other values of Td, they provide an upper bound to the true maximum response of deformation, since the effect of the pulse has been overestimated by assuming it to be concentrated at T equals to 0 instead of being spread out over 0 to Td, okay. It means that what we have done is that here all the loading is being spread over Td, okay, but what we have assumed that this Td is approaching 0, okay. So this has been represented by an impulse loading. Okay. So what we are doing is that we are overestimating the effect of the loading due to the pulse loading. Okay. So over the range TD Tn less than 1/4, the pure impulse solution is close to the exact response. Okay. The two solutions differ increasingly as TD over Tn increases up to half. Okay. For large value of TD over Tn, the deformation attains its overall or maximum during the pulse and pure impulse solution is meaningless because the maximum occurs in its free vibration phase. Okay. It means that if the load duration, okay, is in this phase, okay, then the solution to the impulse loading, okay, and the solution to the actual loading, okay, they are in close agreement. Okay. But when TD is becoming significant, okay, then the solution for the pulse loading is overestimating and it is not becoming exact. Okay. So its validity remains in this region only. Okay. So if the pulse duration is much shorter than the natural period, say TD is less than Tn over 4, the maximum deformation should be essentially controlled by the pulse area independent of its shape. It means that if the loading is very rapid, okay, then this thing is greatly approximated by the impulse loading. Okay. And the maximum duration is essentially controlled by the pulse area. It becomes a case of an pure impulsive loading, okay, where this solutions can be used. Okay. Okay. So we will try to do one example. So here there is an 80 feet high full water tank and it is subjected to a force PT. Okay. So the height of the structure is 80 feet. Okay. The loading is applied at the top and this is the signature of the loading. Okay. And this loading we can approximate being caused by an above ground explosion. Okay. So let us say the explosion is acting out here and this is the signature of my loading. So what we need to do is that we need to calculate the maximum base shear and bending moment at the base of the tower supporting the tank. Okay. The signature of the structure is given by weight is approximately 100 kips, the stiffness is 8.2 kips per inches, time period of the structure is 1.12 seconds and the damping is 1.23 second. Okay. So first we check whether we can approximate this thing using an impulsive loading. Okay. So as a thumb rule, what we are saying is that if it is less than 1/4 of Tn, okay, 1/4 of the time period of the structure, if this ratio is less than that, we can approximate this thing using an impulsive loading. Okay. So our ratio is 0.071. Okay. So what we are saying is that the entire case we can approximate using a pure impulse loading. Okay. Okay. So what we argued here is that if time Td, okay, if it is large, okay, then the total effect of the loading is spread over for a greater length. Okay. But if Td is becoming less and less and less and it is approaching 0, the entire forcing function can be approximated using an impulsive loading. Okay. So as a thumb rule, we are using a value of Td over Tn, okay, as compared to 1/4. Okay. So if this value is less than 1/4, okay, we are assuming that our loading is an pure impulsive type of loading. Okay. So the same thing we are checking out here. Okay. So here the value is meeting the criteria. It means that we can approximate the entire forcing function as an impulsive type of loading. Okay. So what we need to do is that we need to calculate the area under this curve, okay, to calculate the total impulsive loading. Okay. So the loading is from 0 to 0.08, okay, from here to here 0.08 pt dt. Okay. Now we are calculating the respective area. Okay. We are dividing it into the respective zones, okay, and we are calculating the total impulse. Okay. So if we calculate this thing using the trapezoidal rule, okay, the total impulse duration comes out to be 1.2 kips second. Okay. So then the maximum deflection using an impulsive type of loading is given by this equation. Okay. So maximum deflection becomes 0.821 inches. Okay. So here the main point is that using this ratio, okay, we are justifying that the entire loading can be approximated using a pulse loading. Okay. and using this pulse approximations we are trying to calculate the maximum displacement. Okay. So, it is fitting our criteria of less than 1/4, and since it is fitting our criteria of less than 1/4, we are calculating the total deflection using an impulse type of loading. Okay. So, our total deflection becomes 0.821. Okay. Then we are using the equivalent static force that we have already shown. So, our equivalent static force is nothing but my k star times my u dynamic whatever we have calculated. Okay. So, we got our equivalent forcing function. Okay. It means that what we are saying here is that first of all we have the profile of the blast loading. Okay. We are arguing that since the ratio of Td over Tn, if it is less than 1/4, okay, we are going to approximate the entire loading using an impulsive loading. Okay. So, we have done that. After that, we using the impulsive load equation, we calculate the value of the maximum deflection. Okay. Once we got the value of the maximum deflection, we are saying that we are ignoring the cause. Okay. It was actually caused by a blast loading, but we are ignoring that cause. Okay. We are saying that this deflection has occurred due to an equivalent static force. Okay. So, if we go by our static logic, okay, so if P is there, okay, and deflection delta naught is being caused, okay, then we simply know that P equals to K times U naught. Okay. So, we have our U naught, we have our K. So, we are saying that the entire this deflection which was actually caused by a dynamic loading has been caused by an equivalent static loading. Okay. So, this is my equivalent static force. Okay. So, once I have my equivalent static force, I can use the force equilibrium, and this becomes my base shear. Okay. If P is applied out here, my base shear will again be a value of P equals to V. Okay. So, this is the same value, and the moment will be the length. Okay. The moment will be 6.73 times 80 feet. Okay. So, 538 kips per feet. Okay. So, using these equations, okay, we calculated the required base shear and we calculated the required bending moment. Okay. Here one quantity of interest was the damping ratio. Okay. So, in case of blast and impulsive type of loading, normally what we do is that we are ignoring the effect of the blast loading, we are ignoring the effect of the damping. Okay. So, these quantities are an overestimate, these quantities are overestimate quantities of the required loading. Okay. So, maximum response of the linear elastic system to simplified loading. Okay. So, deflections, spring forces and stresses in an elastic system are all proportional to the dynamic load factor, and this dynamic load factor may be applied to any of this to determine the ratio of the dynamic to the static effects. Okay. So, the dynamic load factor may be considered as the ratio of the maximum resistance attained to the peak loading. Okay. So, the dynamic load factor we are defining a ratio of the maximum resistance attained to the peak loading. Okay. So, R is the maximum dynamic resistance and P is the peak load using simplifying the load time variation. Okay. So, in many structural problems only the maximum value of DLF is of interest. Okay. So, normally the maximum value of the amplification is of interest. Okay. So, for the most prevalent load cases, the triangular load as well as the rectangular and step load with rise time, the maximum value of DLF is normally 2. Okay. This what it shows is that this immediately indicates that all maximum displacement forces and stresses due to the dynamic loading are twice the value that would be obtained from a static analysis for the maximum load P. Okay. It means that the dynamic load factor, okay, the dynamic increase in the response to the load quantities is maximum value is 2. Okay. Okay. So, the maximum response of an elastic 1 degree of freedom system for a triangular loading. Okay. So, the loading is triangular loading, okay, and this is the response of the system. Okay. Here T is given by the duration of the loading. Okay. This is T, okay, and this Tn is coming from the system. Okay. So, this is the natural period of the system. So, this is the load quantity, okay, signature of the loading, this is the signature of the system, okay, and the upper curve is showing the dynamic load factor. Okay. It means that U max divided by US T naught, okay. And the maximum value that we can see, it is coming out to be approximately 2, okay. This quantity is the time at which the maximum value of that quantity will be reached, okay. So, if you look into a system, okay, so let us say this system is oscillating, okay, with Pt, okay. So, first there was a forced vibration part, then there was a free vibration part, okay. So, this is the time at which this particular system will reach the maxima, okay. So, this is that time t, t maxima, okay. Time t required for a particular system, okay, having the load signature, having the frequency signature to reach a maximum value, okay. So, these charts are very common in TM5 1300 or UFC 340, okay, and this can be readily used as a design chart, okay. So, for any given loading condition, okay, and for any given system, we can calculate the value of T divided by Tn, okay, the ratio of the application of the loading and the frequency of the system, and from there we can calculate the Umax divided by UST, and we know the value of UST, that is P star over K star, and we can calculate my Umax absolute, okay. And similarly I can calculate the value of the time t at which the maximum value is attained, okay. So, similarly for a rectangular loading, same quantities can be calculated, okay. So, for different cases these different quantities can be calculated, okay. Similarly, we can calculate the same thing for an elastoplastic system, okay. So, here, okay, in elastoplastic system one other quantities comes into picture, okay. So, what is happening in an elastoplastic system is that the system is vibrating, okay, and it is trying to attain the maximum velocity, okay, and the maximum response, okay. But its state, once the deflection is increasing, the state is also can change from the elastic to elastoplastic state, okay. So, that needs to be monitored and tracked, okay, and similarly similar type of curves can be used to calculate the response of the system in the elastoplastic regime also, okay. So, here we are saying the response of the system, okay. So, using the same approximations, the response of the system, okay. So, T is the time period of the loading, Tn is the time period of the structure, okay, and here we are using a curve of Ru divided by P. Ru is the system resistance and P is the magnitude of loading, okay. So, here if the resistance of the system is large with respect to the applied loading, the entire response of the system will lie in the elastic phase, okay. As the response of the system, okay, as the resistance of the system decreases with respect to the magnitude of the increasing loading, the system changes from an elastic curve to an elastoplastic curve, okay. So, here while we are calculating, we will always keep a track of the ratio of the resistance of the system with respect to the applied loading, okay. So, these curves are for the different ratios, okay. So, here there will be a transition from the elastic loading to the plastic loading, okay. So, whenever we have to read a value, we will calculate the time of the application of the loading, we will calculate the time period of the structure, okay, and then we will put it into the, we will also look into the resistance of the system with respect to the applied loading, okay, and then we will have to read from that particular curve in order to calculate my maximum response, okay. Because depending upon this ratio, the system might be in the elastic phase or it can be in the plastic phase, okay. So, this is how we will deal with the elastoplastic phases also, okay. Again similarly here we are calculating, here we are calculating the maximum displacement, we will calculate the time at which this maximum displacement has occurred, okay, and this is for a triangular loading. Similarly, the same thing we can do for the rectangular loading, okay, triangular pulse loading, okay. So, depending upon the different forcing functions, okay, same graph can be used for different types of loading. Okay. So, all these graphs are given in UFC 3340 or TM5 1300. Okay. So, we can directly use this curves for the analysis and the design purpose. Okay. So, here we will calculate the maximum response and the time at which it occurs for a given system. Okay. So, here the signature of the system is been given, okay. Mass of the system is been given, the stiffness of the system is given and its resistance is been given. Okay. The elastic deformation portion is given, time of the loading is given and the magnitude of the applied load is given. Okay. So, time t equals to 0.1 second, okay. Magnitude of the loading is 1000 kips. Okay. Mass of the system is this much, okay. Stiffness of the system is this one. Okay. So, all these quantities are been given. Okay. So, first what we need to do is that we need to calculate the time period of the system. Okay. So, we have calculated the time period of the system. Okay. After that we calculate the ratio of T over Tn. Okay. Then we calculate the ratio of Ru over P. Okay. So, remember this quantity was of importance, okay, because this ratio will determine the phase of the system, whether it is in the elastic phase or is in the elastoplastic phase or it has gone into the plastic phase. Okay. So, what we do is that we get the graph of the response of the system subjected to the this type of loading. Okay. So, the numerator quantity will be 1. Okay. The curve that we need to look, okay, is 0.75 curve. Okay. So, the ratio of Ru over P will be 0.75 curve and the x axis that we are looking into will be 1. Okay. So, let us find out that curve. Okay. So, the quantity is 1 out here, okay, for a triangular loading, okay, and we are looking into 0.75 curve. Okay. So, it is between 0.7 and 0.8. So, 0.75 is not given. So, we will go from here. Okay. So, 0.7 and 0.8. Okay. So, a number between 3 and 5 is there. Okay. So, it is an approximate number between 3 and 5. Okay. So, using a more discretized curve, okay, we can read out this quantity. Okay. So, using a more discretized curve, okay, this quantity comes out to be 3.7. Okay. And the value of Tm over T, okay, using the same thing 1, okay, 0.8, 0.8 to 0.7 curve. Okay. So, this value comes out to be 0.77. Okay. So, x max equals to 3.7 times the value of xc. Okay. So, that value is already given out here. Okay. So, from there we can calculate the value of x max and the value of Tm. Okay. So, this way we can handle any given problem. Okay. Only thing what we need to do is that we should be able to calculate m star, k star and the other quantities, and then we can directly read from the curve and calculate the quantities of interest. Okay. So, in this way we can handle any given problem. Thank you.